Okay, just quick again recap. Fine. So the whole idea that we were trying to solve after deep learning was the recurrent neural network. Why it comes up? Why somebody would create a neural network with an idea of recurrence? Okay, why they would is because the whole idea is to use recurrence to predict the next point. Here you see there are points which you have seen earlier also. There are points which are in time, which are stretched in time, okay, which are spread in time for a particular time. T0, this is happening. T1, this is happening. T2, this is happening. T3, this is happening. Are you able to see my cursor? Pointer, mouse pointer?
Yes.
Okay.
Yeah, yeah, yeah.
Yes, sir.
Yeah. So, and this is happening, and then at a certain time, this something else is happening. Right. So, oh, why am I not able to click and get? Okay. Hmm. Okay. Hold on. Let me open it up again. Okay. Right. So we are able to see this point, these points. Of course, what you want is to be able to predict this particular point, the black one, the last one, which is here. I want to predict that. That's my contention now. That's my requirement of the project, that I want to predict this point. However, you see here, this section here on the right side, earlier we used to do it as a linear regression problem. But when it comes to linear regression problem, that's the linear regression problem will see this whole pattern, whatever pattern we have, this whole pattern in linear regression will be seen as a curve fitting pattern. So you just want one line, we just want one line to be an approximation of that algebraic relationship. However, when too many things are changing so much and when you want to zoom into one particular section, this line which is there, it becomes a very big approximation too far away from the reality, which means what, there is too much variance in this data, too much variance. We can't use simple linear regression. So what we thought, or what the scientists thought, was let us predict this based on what this previous point is saying, but this previous point should be predicted based on its previous point. So it is more of a recurrence where you remember why the previous point came to be that way. So you see, I have two dots here, one red, one blue. What it signifies, this is important here. What it signifies that to predict this point, the one which I have selected now, to predict this point, I am going to use the reality and the prediction, the red one, which is actually the prediction from this state. So this particular second blue point predicted that the next blue point is at the red point. That's what this blue point predicted. Now, can we both use this red point and the blue point to predict the next point? But it won't. It'll predict, but it'll give another prediction which is here. If it is also, if it is almost same, then it is fine. But you might get up a little, a little different. A minute difference will be there. So that is why the recurrence comes up, and it works very well, especially in time series data, stock market, and all this inventory management, logistics, where too much variation is there. We are trying to capture the entire variation as a state machine, not as one general function like how we do it in linear regression. You see, on the right side, you see, we don't want to do this. We want a very, very accurate system. So the same thing, what you're seeing here, you see on the bottom here, on the, below that curve, you're seeing this red line here, correct? These red lines connecting. So we build a recurrent neural network where each one is being passed to the next one, so that we keep predicting the next state and finally get to this state. Means my requirement is this. I clearly tell, look boss, see, this is my vector. These are all the points in time. Okay. And I want the next point. We are saying that to it. Okay. And when it understands that, achha, this is what this person needs, it will build we should build a recurrent neural network in such a way that this particular point, the one which I'm interested in predicting, the last one, this point's prediction becomes a function of all the other states before it. That's why the recurrence. Okay, so we're going to see that in action. So we want to just make sure that we understand this, correct? So, but obviously, we want to have a weight and a bias. You look at these weights and biases as the ingredients of that function, which is then going to get into activation function, and that activation function will be successful at predicting the next point. From there, you multiply it by another weight and pass it on to the next recurrent neural networks phase, which is responsible for predicting the third point. Okay, then so on, so on. So you keep on moving like this, you'll get the last point. The problem here is you are either adding the bias or multiplying it with weights, right? So here you are multiplying it with weights, and if you keep on multiplying like this here is just 1 2 3 4 5 6 7 8 layers of multiplied weights on top of each other. This structure comes out like this. There is no other way they would have imagined it in the first place, right? The structure comes out like this. So what problem was happening is it was not converging at all. This whole point was getting missed. Why it happened so is because the gradient, which is supposed to come here. See, when I say what is the next point, okay, see how it thinks. When I say what is the next point, and I say look at all these points in gray and blue and all this, right? 1 2 3 4, look at this and predict the next. What it does is it will say, acha, so this is your pattern, so let me first use this point here, the first point. Let me first use the first point and get to the second point. Then let me use the prediction of the first and the reality of the second to predict the third. Right? So it builds, it says, okay, let me first get this to this, this to this, this to this, this to this, and so that I'll be good at predicting whatever point you want next. That's what it is saying. Okay. How does that turn out as a mathematical structure? The one which is below you. But this structure fails because of exploding gradient or vanishing gradient. It explodes when you have weights greater than 1, and it vanishes when weights are less than 1. think somehow Gmeet takes a lot of resources. What else are there? Wow, this is bad. Some issue on this. Let me reload it. I'll be back. Okay. Anyway, I freed up some resources. Let's get back. Okay. Are you guys there still?
Yes,
Yes,
sir.
sir.
Okay. So basically, what I was trying to say is, when weights becomes more, it will explode, and when it is becomes less, it is going to vanish. So we have seen that. I'm not going to get into it. A visual representation of this is, say, as a read through, read with me here. To predict this point, we had to predict this point. And to predict this point, we have to predict, follow the color, okay? This point. To predict this point, now you follow the blue color. To predict this point, you have to predict this point. To predict this point, follow the last one, predict this. So it goes like this. That's what this means. Okay? Getting it's recorded, so you can watch it again, you'll get more. So basically, now what happens is, when data points are large number, huge in number, we end up using too long memory sequences. What if we separated prediction into two separate ways? One is short term memory, one is long term memory. So when what I'm trying to say is, in the long term, only those critical context is memorized, and not everything that is. So every time you'll have a short term memory. From here you will have this called like a sliding. Okay, there is a slide which happens. It's a window. So from here to here, first the same thing what you're seeing here, no, this whole curvy thing. This happens here. Next, the window slides. Will come here to the next point. Next, it will come here to the next point. Next, it's going to come here to the next point. Why it is doing like that? Because it is like, that's where the validation set comes up. Okay, so you have to be able to be very strong, very much assured that you're actually able to get to the next point properly. So there is a slider here which comes up, in your LSTM. So you see there are two layers here, right? One is a short term, one is the cell state, which is the long term, right? So how, okay, this is how the end of the uh, LSTM model looks like. The blue one, the green line here, let me explain the green line here. Let's break this picture down. Okay, so this multiplication factor and additive factor, which is a part of the red line, is called the cell state. This whole red line is just the state of that entire cell, wherein you have the multiplication factor and an additive factor. Everything boils down to multiplication and addition. Okay, always. Everything you see, all computation, everything finally has to boil down to variables getting multiplied or added, correct? Or subtracted. Divided means subtracted, right? So basically it's just addition and subtraction only. These are the only two operations. Everything else is on the top of it, but the fundamental operation is add and subtract, right? So how much to add, how much to subtract for that variable, that's what the whole game is. Okay, so here you'll decide how much of the long-term memory to retain. Of course, we realize that which one to retain, what is the critical word that needs to be retained. So this green line called the cell state represents the long-term memory, which is modified. The long-term memory is modified by additive factor and a multiplicative factor, which in turn helps you decide how much long-term memory to retain. That is the, you know, structure. Notice that there are no weights or biases that modify the cell state. That is how you get rid of the gradient vanishing or exploding gradients. Now the short-term memories are represented by purple line below. Notice here we have weights. Short-term has weights, long-term won't have weights. Learning requires weights and biases. The real learning happens here. The cell state is only going to, after you learn, you make sure that you decide how much to retain, right?
Mhm.
You
Right.
understand, right? Dharmendra, you were saying
Yes, sir.
something?
Yes, sir. Following, sir. Right.
Yeah. So imagine you're a researcher at a science lab. Every day you do experiment, jot down ideas, get feedback, work towards a big project. Imagine that, right? Every day you're a researcher. Every day you do a lot of experiments. You jot down the ideas, you get feedback, and work towards a big project. That's what you're moving towards. Example, I'm giving an example so that you can understand long short term memory. Short term memory is your whiteboard. Okay, quickly, like how I'm trying to do here, whiteboard. Use it for notes, numbers, quick sketches, things that you help that's going to help you with the task right now. But the long term memory, after we do all these exercises, then we decide how much of this note should go into my fair book. It's, in schools we used to have, one is neat book, another one was experimental book. What
Yes. Book.
rough book, yeah. So rough and
Right.
neat. So the rough we
Yeah.
write, and the neat goes only the main points go in the neat. Correct. So
Right.
like that is a long short term memory is that only. One, there is rough work where it is experimenting which one is important, which one is not important, getting all this. The the long term memory will contain only those which make sense. Now to again go back a little bit into a technical way of looking at it, the short term, the purple one which you saw is called the hidden state. The long term is called the cell state, right? Simply they have to name something. I mean, it may not be intuitive. It could have, uh, should have called something else. I feel they should have been a little more creative. A hidden state I understand, but cell state I don't know why they would call it that. But anyway, they call it cell state. Let's agree. All research papers mention it as a cell state, so I don't even want to attempt to change it. However, the three ingredients of this network, the together, like here you see this, what I showed you here, see this one, right? The three main aspects, how they have divided engineering, how the engineering is done. Every time I do this it just goes a little bit, right? So there is forget gate, there is input gate, there is output gate. Okay, let me just let me just this is an example which I created. I'll show you. Something like this will come up. See the forget gate, input gate, candidate, and cell state. This is an example I'll show you later. Okay, this is something extra I added to this lecture. So anyway, so now just understand forget gate, input gate, output gate is here. So forget gate, input gate, output gate together makes your LSTM network. Okay. Now why two memories? Let's say you're reading a sentence. Let's say you're reading a sentence called after drinking the spoiled milk, he felt. Okay. You tell me. After drinking the spoiled milk, he felt what? What do you think ideally should come there?
Mm. Ill or not well.
Viva? After drinking the spoiled milk, he felt
Uneasiness, like
sick,
stomach ache.
uneasy, correct? Everything correct?
Yeah.
Right.
Now you guys tell me, was the negative word,
Mm.
the negative word has to come there, correct? A negative emotion has to come there. You know
Right.
that, correct?
Right.
Right. Right.
That
Right.
negative word God gets influenced by the word after. Does the word after affect the negative word?
No.
Does the word drinking has any correlation with the negative word?
No.
No.
The word the
No.
No.
Not.
milk,
No.
No.
he felt, no, right?
No.
Which
No.
is the most important word which is going to affect the occurrence of the negative statement there?
Spoiled.
Spoiled.
After.
So now you know the spoiled has to, so instead of understanding all of that and retaining everything, how does it pick up
Mm.
the context from past data? Wherever it has understood, it has understood that when the after and drinking the everything is fine, but the word spoiled wherever it has come, this negative statement wherever it has come, the felt, after felt, then another negative only has come. So that is how it learns. This is just a NLP version that I'm NLP example I'm showing here, so that you understand both time series and NLP version of it. NLP is also nothing but time series only. Okay,
Okay.
so you see, eventually everything is a number series only. This whole thing gets converted to a matrix. You've seen that matrix in
Yeah.
life,
Embedded.
where,
So in the example also you have shown, right? The embedding.
yes, and I guess even in your uh, what is that? Hmm. Here you see, you've seen this in knife base, correct?
Mm.
Ah, yes.
Yes. Right.
Text becomes numbers matrix, then you'd use inverse document frequency, then TF IDF, the multiplication of term frequency and IDF will give you this matrix,
Mm.
correct? Here in this
Okay.
matrix it is giving a value of the particular word. The word language has high value here, natural has high value here, Python has high value here. The word like and hate, but also somehow come, okay, but probably is because it is a condition, right? But, so but
Right.
has a, it sort of differentiates between, okay, I like this, but so as they
Right.
say,
Right.
everything you say before but is bullshit is what they say, correct?
Right.
So anyway, so they it kind of is an important segregator, and somehow, and also in text 3 it has got a high value, but fine. So this is how, that's why I said, whether it is time series or image or anything, eventually everything should get back to what? Eventually everything should come to what? Numbers.
This numerical work. Right.
Numerical. Correct. Why? Because your computer can only understand numerical, right?
Numerical. Right. Right.
And if you think about it, if you simply think for a while, just sit and think. If your computer is what does your ALU do actually? Arithmetic logical unit in a computer. What does it do? It is only good at
And,
doing digital addition, digital subtraction. That's all.
right.
Is there any other magical operation you have trained it, or logic gates? Correct. Anding or logic gates. Correct.
Mm-hmm.
And, or, XOR, NOR. Correct. Logic
Yes.
gates and addition, subtraction. Correct. No.
Right.
Everything else is an abstraction on the top of it. Vaibhav, you agree with me on this?
Yes.
You think today. Just
Oh, oh,
deeply
oh.
think that every problem, if it is going to get solved by the computer, it will just be repeated addition or subtraction.
Um,
Right.
Just the drama in which you will. So, which one is the one which will contain all the drama that you create? Algebra will contain all the drama that you will create for it. No? Correct? The algebraic
Correct.
equations are the ones which has been created to contain this drama that you will create to get to the prediction. And while training, you need calculus, but calculus also is going to be a part of your algebra only. Correct? Are you able to get to that point? What I'm trying to explain, right? So basically that's what this is. So if you have only one memory, like in the vanilla RNNs, RNN is the usual simple RNNs. You would either you'll forget important long-term context too quickly because it will explode, or you would have to memorize everything equally, where you not give any, but you not extract the context out of it. Only when you set it up as an LSTM, long short-term memory, only then can you expect that, hey, one particular context has been cornered here, around which the next text has to come. That was something which is like amazing. So later on, because of course I'll not be able to go into the whole depth of it, but let's see if we can do transformers and attention vectors now. Since I've made a delay for you, I've already told you that I'm going to give you more than what we had expected. So I'm okay with it. I'm going to give you all that. Okay, I'll teach you. So let's slowly build this. Maybe this is the third time. I think what Dharmendra, you're listening to this third time or second time? Second time.
Second time, right,
Second
sir.
time. Yeah, for Viva it is first time, but fine. It takes time. I will not expect. Uh,
Right.
so real world metaphor in AI. You can think of cell state as a hard drive, stores deep context over time. Hidden state as a RAM, fast access working memory that gets refreshed often. See, this is what happens, correct? Cell state is a hard drive, hidden state is a RAM. Another example for it. Okay. See, you I for when I understand, I understand. But when I have to make you understand, then I'll also use ChatGPT. I'll also make it write different kinds of programs, just so that we can discuss it visually. You can also do it. Not that you cannot.
Yeah.
You can also do it. But it requires some kind of knowledge, some kind of knowledge to, um, for example, I'll show you. GPT, in GPT, I think I have. Let's see. Let me see. I had done a research. I'll show you that everything cannot. I don't have it here, I guess. 100 simple time series using LST. Uh, ah, okay. Is it? Okay, I don't have it here. Basically, I had asked AI some question. Okay, so it gave an answer. I asked, digged in. It gave an answer. Fine, everything was fine. But later, then when I asked it to think in a different way, then it gave the right answer. So we need that.
Actually,
I'll show it to you later. Right now, I don't have it.
okay, okay.
I'll show it to you later. This is supposed to be here. Anyway, so I'll find it. I'm not able to find it now, so I'll find it. Anyway, so where were we? Huh? Let's understand the phases intuitively. So you see, basically, you are looking at a diagram which looks like this. One of the points comes in as the previous input. The next input comes in here. Okay, so we both take this, we multiply this by a weight and have a weight and a bias here. Together, one more bias is anytime you can use another bias, extra bias. Here, this is a simple structure. Don't think that always this
Okay.
much is used. Inside, it can have different biases. You will just ask it to set it up, it will set it up. Okay. So you have a bias, then an activation function, and from all this comes out one number which says this is the percentage of long term to remember from this. This whole network will isolate what? It will isolate the word spoiled and filter everything else. If you are going to feed this, that text to learn, it
Okay.
remembers the word spoiled. It remembers that spoiled has to be remembered in the long text. Okay. So it's understanding, it is slowly getting that whole idea of what is happening. So as
So,
hello,
so is
yeah.
it like because we have the sigmoid activation function, so for all other words in the sentence, the output will be activation function, output will be 0, and for spoiled it will be 1. Is that how?
Can't you can't think like that.
Okay.
It's not a word anymore, you see. Don't think once it goes inside,
Okay.
don't think of it as a word.
Uh,
The word
uh,
doesn't exist anymore there.
right.
This exists.
Right. 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 Right.
This
Right.
matrix exists. So it
Uh,
will only look at this point and it'll say, okay,
uh,
when was the last time this much weight and the next word having that much weight? Only it is looking at numbers.
uh, uh,
Okay, so don't literally take, don't try to literally map it to that
right.
word.
But,
The word is no longer existing. I'm just giving you, of course, my mistake. I'm sorry. I should take it back. Gets converted into TF-IDF matrix. Now there are other matrices, transformers, encoder, decoder matrix comes up. So fine. So
okay.
the
Right.
so here in this case, I'm just trying to give you an intuition. Okay, intuitions of. Next, what we did.
Sure.
So next, what we did was we got this data set. So did Vaibhav get a chance to download this data set?
No.
It was there in the this one
Discord.
chat, Discord chat. Both the code and this data set is there in the Discord chat.
Okay, I'll download it now.
Okay. So let's say I'm going to use this data set now. Let's say I'm going to use this data set to demonstrate LSTM for you. Do you think I'll be using the entire data set or entire column of it? I'll use the data set full, but will I use all the columns here? LSTM is more like a time series problem. So I am only going to, in this particular weather data prediction, I am going to choose one of the columns. This column I cannot choose because everything here is state. So let's say I put, for rain I put 1, for sun I put 2, for snow I put 3, and for drizzle I'll put 4. So you see 1, 2, 3, 4 will repeat here, correct? Correct or not?
Right.
So do you think this column will be an optimal column for me to apply recurrent neural network? Nothing is you
Not
know.
this column, but once you convert it to 1, 2, 3, 4, then yes.
Okay. But ideally, we'll try. Let me try. Let me try it on my end and then see what happens. But in this example, we have taken this. We have taken around, this has around 1461 data points, I guess. Okay. Yeah. The first row is taken as 0, so fine. You have 1461 data points. We are going to take all these data points and we will try to predict what will be the max temperature on the next. So we will train an LSTM model to learn this pattern. That's what I'm trying to say. Okay. So if I give you this later, once the whole training is done, if I give this much, it should be able to predict this.
Mhm.
Okay. Then if I give this much, it should be able to predict this, or it should be able to predict the
So,
next. It will be able to
so
predict
the
everything
training
because it has
is
understood
max,
all the
no?
states. In between all patterns, where from here to here, from here to here, from here to here, from here to here, it just understands everything now. So that's why I
Mhm.
said we are going to do this sliding.
So,
Ah, yes.
will you be giving like all the columns for training or the training the model or just one column?
Only one column.
One.
Okay.
Okay, like this. It will just. This is the demonstration of long short-term memory. It takes in only this kind of a problem. Where is that? Okay. So we in this example we have used only one because this I'm talking about time series. I have to show you time series, correct? So what
Yes.
is the equivalent of this example? What is the equivalent of this? This is all temp max in time. That's all.
Mhm. Yeah.
All max temperature. Think of this whole series as all these points as temperatures and on a particular yesterday, today, tomorrow temperatures. So that's what is here. Okay. So we build this by loading this data point here. Once we load it, we get this data set. Okay, we're using pandas, you see it. Then you check for how much is, whether there is any null. So there is no null value. Everything is fair, data is good. Then you take the training set from DF, which contains all this. You take from using iloc, you take two, between 2 and 3, 0, 1, 2 and 3. So the second one. That's what it means. Now, if you check what the training set is, so it has printed this year. See, 12.8, 10.6, 11.7. 12.8, 10.6, 11.7. The first three. The last three are 7.2, 5.6, 5.6. You want to check? Let's go and check. Hopefully it is that. Yeah. See? 7.2, 5.6, 5.6. So the whole thing is given. So validated. That is what has been loaded. What has been loaded? Temperature max. To get to the temperature max from a DF which contains all the table, you did 2 comma 3, you added it in. Then the length of the training set you already seen. Right now, I told you, right, we want to set that window size. This window size. How many windows are you going to shift from here? So I am setting window size as 5 here. Here I have 5, otherwise because I don't have a long sequence here, no. Otherwise I would have set it like this 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 10 window size. So it will go like this. Next 10. Then next 10. Then next 10. So it goes like this. And if there are 1040, 461 data points, it will again be taken as batches, like how we did 32 per batch. It will again be taken like that. Okay. So to set that window size as 10, after setting the window size of 10, you will have the X train and the Y train with you. X train is all those first 10 points. The Y train is all the remaining points. Okay, so whatever that particular point is, minus of that 10 to the I, the first 10, and remaining I comma 10, whatever is remaining from there I comma 10 is the training, the Y train, the X train and the Y train. Okay, so you want to get the Y from the X. That's what it is. So here we have used that function. X comma Y is equal to df to xy, which has been defined here. Df comma window is what you set here. Window is equal to 10, right? And then this happens. Once you get the X and the Y with you see, once you get the X and the Y with you, just try to print length of X, length of Y. So minus 10 is already happened here. Okay, so that minus 10 which was there, which it's already removed. Now once you get this is fine, but once you get this inside this we need the training set, the validation set, and the testing set. So in LSTM you don't see just training and testing. So this is how things change from machine learning, classical machine learning, to deep learning, because every sequence, every window has to be understood, right? So there is an intermediate validation set also. That's what this is doing. I guess this must be fairly simple. The first 800, from 800 to 1200 points are validation. The first 800 are training. The remaining from 1000 remaining are all testing. That's what it says. Okay, so that's what this explanation is also saying. Now we want to reshape it to add new dimensions. This X train and X val and X test has to be reshaped, and to reshape it you are doing X train of shape 0. Why is this done? Dharmender, any?
No, no. Yes, sir, I tried. I could not understand. I didn't try Chat GPT to get the answer.
It's sort of, this, to explain this, it's a little, it's more like a linear algebra transformation that it is after actually.
Is it like done for so that matrix multiplication becomes easy and we get a single output as answer?
Sorry?
Is it done so that we the no matrix multiplication will be easy? Anything like
Yeah,
that?
yeah, exactly. That's the correct intuition. That's the correct intuition. So that the matrix dimensions are matching without adding extra
Okay,
information.
okay, okay.
Simply we can't add numbers. Okay. Otherwise we are losing that information, correct? If you simply add numbers, we'll lose information. But just to make the matrix multiplication possible, we do this.
Okay.
Okay, let me run through this now. Later I will create one video which explains just this aspect, just this one only. Okay, because it's not a simple code, it's a long code. Inside every cell there's a lot of stuff that has to be understood. Okay, so I will create this extra bit of linear algebra matrix um, perspective. One second. Okay.
To add to that, sir, I also did not. I tried. I did not understand this return sequences.
Which one?
Return sequences. When we add a stem layer, right? We have parameter return sequences.
Okay.
That one also I didn't get.
Did you try doing return sequence false and check it?
Um, I didn't try. I understood like false is used just to when we are at the output. I mean, we just have one. We have to make only one connection from the previous layer. So in that case, we use false. But I mean, I don't get like what is the logic? I mean, I didn't get
Basically,
anything actually.
basically, see, this return sequence is this. This. This, you see, for every state, if at every stage you are adding this one, no?
Okay.
Here, every stage. So you're saying I want input from every state of the hidden state, not not just the final one.
Yeah.
Means I want every data point to be accounted for. You see,
Okay.
because every hidden state was this only, right? Every where you see, that is what it is learning. No, it is learning from this to this to this to this, correct?
Right. Right.
All the weights are getting you know
Okay.
learning using weights and biases happening here. So I want
Right.
everything to, basically, when I say return sequence is equal to true, you're saying I want the complete sequence to be learned.
Okay.
That's what is this. Anyway, so wait, let me just, I had one example. Let me just see if I can code it and send it to you. I think I have an example. Mhm. Hmm. Let me just grab that. Let me grab it. This is from here. This is from here. Hmm. I'll I'll so anyway, this intuitively understood what this means, right? I don't have that sequence with me now. Some other project had it, so I was just searching for that other project.
Okay.
This
Okay.
return sequences is equal to true means you have to go and keep all the sequences intact is what I'm just trying to say.
Okay. Hmm.
Not able to find it. We'll search also. So where is that? Okay, we are here. So we reshaped all the X train, the X val, and the X test. Everything we've reshaped. Now we build. This is where you build the building the recurrent neural network of the type LSTM is. So LSTM is a kind of recurrent neural network. So you say from keras dot models import sequential. It is a module which whole thing is seen as a sequence. So under sequential, you'll use sequential here later. Import sequential. We're going to use sequential to create the actual regressor. Okay. So we'll just make this. We're going to bring the object of this class. We're going to create that object here. From keras.layers, so you want layers. In layers, you have dense, LSTM, and dropout. What is dense doing?
Hmm.
You remember?
Is it like connecting everything from the previous to just bring it to one neuron?
Correct, because the output is only one point at any given state. That's what it is saying. So it is saying I don't want you to predict 2 points or 3 points. As a dense means you learn everything so that you can predict the next point only. That's what dense means. So when you put it as dense, then all the things combined to all the learning, all the drama, all the learning combines to predict just the next point like this. The next point. See the next point here. All you have to learn, all this window, everything, all learning is to predict the next point. So you see, so this will be a very densely packed network like this, which is here, a very densely packed network. Okay, all this densely packed network eventually should predict one point next. So that's why it is used as dense. Then you are importing dense, you are importing LSTM, you're importing dropout. We'll use this, okay, like 20% of the points. So here you say 50. So basically, once you use all this, you have the dropout, you have the LSTM, you have the dense, you're all getting it from this keras dot layers. This keras, what is this keras doing? Keras is the
It's a wrapper on top of the TensorFlow.
Correct. Keras is a wrapper on top of the TensorFlow. TensorFlow is there to implement deep learning for you. Correct?
Right.
Right. So deep learning, TensorFlow. Just hold on because this class may go a little more longer. So I'll just message. I had another meeting coming up. I'll just extend that meeting by 15 minutes. Okay. So you have units is equal to 50. So what 50 is going to do here is, see, we are creating the first one, the hidden states are being created here. Okay. For all these hidden states, we are setting that this hidden state should, throw out, or after it has to, we can say it has to learn to output a state vector from the hidden state vector, and that hidden state vector's length max can be 50 for each step,
Right.
right? So that is what it is trying to. So one second, I'll just message. Now you have the input shape. This is again done how you want to put this input shape. This is again done that you will take this extrains shape and sort of have a time. This is more like a time steps and features. The shape is time steps and features. The sequence of the shape. We have time steps and the features. So that shape is set here. So time steps and features where you return the sequences with 50 hidden state vectors at every stage. Then you can drop out 20% of the data at every stage. So this is one LSTM hidden state that has been created. Like this, we are creating. Okay, regressor dot add this, then regressor add this. Here you are not setting up any input shape. Here you are not setting up any input shape. Here you are not setting this. Then you have the output layer. This output layer dense units is equal to 1. All of them combined to become units is equal to 1. This whole thing from here, this is your, this section, what I have done here is all of this that is happening. Later you will put regressor dot add dense units is equal to 1. You're going to get, basically for any given time series data, you have to just see this. Later you can study, we can understand in a next discussion, we can understand why only 4 were there and why this got deprecated. Okay, why we didn't use this, why again we are not using this, why we are not setting any return sequences equal to true in the fourth line. We can understand that. Okay, first let's do one run of the code, then we'll come back to the more detailed explanation of that code. And then you have regressor.compile, because this is where the compilation happens. So until now you're setting up कि मुझे what all I need. First you shaped up your X train, X validation, X test, because you need to train, then validate, then later we will test it. Testing data is separately taken, validation data separately taken. This one here you see train X, this comma, there are three elements here. Okay, these three elements is more like samples, input, and the shape. So that's what that the whole sequence comes out of it. In fact, wait, I have it. I'll just show it to you. Don't get it when I want it. Okay. Okay, let me just put it as a comment here so that I can share this. So basically, you had samples and time steps. We reshaped this into samples, time steps, and features. So you have moving on. So we created this, then we built the RNN, then we got the regressor as sequential, then we set up all these LSTMs, then we decided, okay, we told clearly that regressor, which is of the type sequential, should have the dense module whose work is to convert all this linkage into one unit, which is your final output. Right, so basically you are setting this up as one because you have only one variable in each of the training that you are using, right? Now regressor.compile optimizer is equal to Adam, loss is equal to mean squared. You already know I've discussed Adam optimizer. This is not the usual gradient descent optimizer. It is much more advanced. It takes care of a lot of uh, problems which comes up. We have already discussed this. We move forward. Then we use all this in inter-training parameters that needs to be tuned. So we said TensorFlow dot keras dot callbacks, from callbacks import model checkpoint and early stopping. These are modules which has the control when this is happening. Okay, when the model is running, when the training is happening, these are the modules which has checkpoints on it, because see, mean squared error is being calculated, root mean square error is being calculated, and Adam optimizer is being inside that. These callbacks will happen again and again. Model checkpoint is where which uses your validation set. Okay, and early stopping, if at all there is early convergence, it will use this. Okay, we have all this ready. Now we create something called history. We can name it as anything, but basically, as any model is deployed or any training starts, the start of the training is where you fit. So you say regressor.fit X train with Y train, where validation data is equal to xval and yval, epochs 100 with batch size of 32. So every time it will take 32 data points and run through that entire learning. And for that learning, 100 times you can go to and fro, do decides and stop at the best weight. You can, use it less, because at some point of time you are actually here, your validation loss is still high. Maybe you can run epoch for 500, but let me see if I run epoch for 200, will it? Mm, in the meanwhile, while it runs, history is equal to regressor dot fit x train y train. You are fitting the x train with y train where, see, 1 or 200 is starting now. It's slow. Everything is, too many things are running, so it's slow. Maybe I can close my website also. So loss is high here. More, if I run it more number of times, then maybe we'll converge at a better. Let's hope so. Okay. Earlier we saw what we saw. It ended at around 9 point here. No, validation loss was around 9. Hmm. So see, you have this loss. This loss is being calculated. This one, right? This loss. It is being calculated by your mean squared error as a part of the training. Okay. But this validation data set is something which, between this and this, is the whole training happening. Okay, so that's how you should be thinking of it. It's not. Are we going to see it increase? Hmm. Didn't do much change. Even if you see somewhere it was increasing, decrease, and then it just increased. So I guess that is the max it can learn from this data set. It cannot perfectly adapt to all the sequences, but this much loss will be there. So anyway, let me go back here. So this is where you're. So think of it like this. Finally, the regressor has to fit your X train and Y train and your validation data set. It means that from the given data, you have to have your X train, you have to have your Y train, and you have to have your validations. And then you want you want the regressor to fit it, but you want the regressor to have certain, this regressor. Okay, this regressor is coming from where? This regressor is coming from sequential, from keras.models import sequential. You are going to set up all the attributes of this regressor, where you'll say this is what my long short term memory should be doing, throughout 50 states. You have to remember that this is how the structure will be, right? Return sequence is true, input shape we'll have to put it here. We'll learn more about this and this in a detailed hand calculation way. Simple example, we'll learn more about it. Now, once you have this, let's say you took history, the history can be changed. I mean, we can just rechange this name, but history start history is also saved in here. What is this history's history? This, the whole thing what has happened here, no? how the losses and validation losses changed. That whole thing is here, the loss and val loss, how it changes. We'll need it later to print this loss versus validation loss. Earlier, how the losses changed, how the validation loss changed. Slowly, after a while, it see this, it almost followed, then it started departing. So it was, this is the learning. This is how the learning has happened, is what it is saying. If you keep on adding, now if you say instead of 100, 200, if I say set the epoch to 1000, you can set it up. I'll send you this code. You can just set it up and see. I'm expecting at 1000, this will again depart. The learning will go away. Okay. So I'm expecting that. So you have all this. So again, you had changed that dimension, right? So you're again flattening it. Whatever you had changed, that matrix before reshaped, whatever you had reshaped, you are going to just flatten it now. Okay, so then you said regressor dot predict x train. You flatten that prediction and put it into train predicted, right? Then regressor dot predict, use the x val, put the x val. Now this is train prediction, means prediction based on the training data, prediction based on the validation data, then prediction based on the test data. So for each of that, you have the number of times it has epoch, right? So how fast it has converged. You can check that how your actual and your, so this is just plotting. So you can learn this plotting or understand the code of the plotting on your own. So predict is equal np dot concatenate train predict val predict and test predict, all in pred it is. Okay, so you concatenate all these values. Then you have data frame from temp max dot copy, which is a def predicted directly the whole from pd dot data frame df temp max dot copy. So you just take that copy and put it as a def predicted. Then you have def predicted columns as actual is equal to actual. So you have actual here, see this actual, right? And then you have def predicted the window size, that you have everything after that window size, right? The window what you have given, that's what your actual pred is. So now you're saying the predicted def preds predicted is your pred, right? So all these things are actually shown here. So you fix that plot sizes here, then you plot validation result. You're saying, you're just putting those validation results here, then you're putting test results here. So this is the we had three sets. One is training, validation set, and test set. On validation set, this is how it is moving, and on the test set, this is how it is moving, is what it is being shown. That's why you have the points from, you're supposed to have it from, but we have taken the entire, against, we have plotted it against the entire pred, right? That's why we've taken the entire pred here for def predicted. That's why def predicted has the entire pred value, in leaving all this value as your um, right. So finally, this is how you are going to check whether your machine has learned this whole set what is here. In this part of the or the section of LSTM, what we have just seen is the mapping from here, right? This mapping coming on to this. Now once you understand, you try to make you watch this video again, try to make sense, then you will start having questions. Once you start getting interested, you'll start having questions of what each one is doing, what this stands for, what this stands for, and what how this whole thing is changing. You can follow this up. You
Right.
yourself check this, check this, check this, what is happening, why this is changing. You can check and it'll immediately make sense. This part is easy to make sense of. Okay, because this is where the plottings are happening. The whole thing, learning happened here. Where is that when you fit, right? Only thing you have to make sure is why you did the reshaping, and why did you do the free fat flattening again here. Here, why was it required for the regressor dot predict function, which is going to do the prediction on the extreme? All that data needed to be flattened. Why? Because you need to flatten it so that you can plot it here in 2 dimension. In training, it requires it in a different dimension, because it's all linear algebra, matrix multiplication, and weights, right? It has to remember the different weights for it. So you will use it like that. So you'll flatten it back to get this back. Okay. And see, if you don't understand it, don't blame it. It's not because you're not intelligent. Okay. And it is because these concepts are not some silly 10th or engineering. These are very advanced. In this simple small code, there is at least 50 years of research all put here in one shot to build linear algebra, to do all this, develop pandas out there, develop deep learning, so many things, all structured in one thing where this learning has happened. Now, what I want you to do is understand what happens if you don't use validation set in LSTM. Okay, with this knowledge, understand what happens, then understand how the flattening and the reshaping is happening. Code is with you, the data set is with you. My boy, we have the code and data set with you.
Yes, sir.
Yeah. So again, we will redo it again. I will bring it. There are, see, this one I have it. See, I've already built. I don't have the time. Just I wanted to show you how sigmoid, concatenate, tan H, everything that you're seeing for this example after drinking the spoiled milk. Okay, afterwards, each word, what is happening to it, right? And how this, the state. You see, if you zoom in, you'll understand. This is your milk spoiled the drinking after. So everywhere you will see the correlation for value 1, for value 2, for value 3, for value 1, everywhere the spoiled. How it gets selected, the word spoiled finally comes up here as the one. See this at cell state, what finally is remembered.
Right, right.
So we'll understand slowly. Okay, we'll understand. It's gonna take time, right? We'll be here until we get it. All right, one code properly end to end understood with all flawless, all ambiguity out. It will pave way for other, because here in this only you have to go and do so much research, so much of matrix multiplication, what is flattening, what is reshaping, why it happened. You have to do your homework from there, and we'll discuss and we'll get to that. Okay, shall we close for today?
Yes, sir.
Yeah. All right, thank
Yes,
you.
sir.
Okay, thank you. Tomorrow, Vaibhav, again, just make sure that you fix it here. Okay,
Right, sir.
right. Okay, bye.